Lesson 5.6 is all about radical expressions. There are a couple things I want to go over just to clarify. This little wavy symbol here is our radical symbol. Anytime you see that, that means we're initiating a radical expression. The number out in front is our index number, and that's important because if we don't have it, if we just have our radical symbol alone, that implies square root. So it's like having an index of 2. So the square root of 25, we would say, is 5. But let's say I had a 64 in here. Square root of 64 is 8. But let's say we wanted to change the index number and we wanted a cube root. Well, going back to our table from 5.5, we know that the cube root of 64, or what times itself 3 times, what cubed to get 64, that's actually going to be 4. So it's important to know what index we're working from. And again, if there's no index, it's implied that it's an index of 2, or just a square root. The number underneath our radical is the radicand. In this case, it's 64, in this case as well. So now that we have that clarified, what everything is called, let's go over a couple little properties here that are going to be very useful for us. If we have radical of any index of a product here, so a times b, we can split that up then into the nth radical of a. So again, if our radical is 3, it would be the cubic root of ab would get split down into the cubic root of a times the cubic root of b. So we're basically just splitting these two radicals up, making sure that they have the same index as the original. A way we can kind of show or prove that, or at least give an example, is if we have the square root of 36, which we know is just 6. 36 is the same as 4 times 9. So we broke it down then into the radicals with still the index of 2, which is kind of implied there. We broke it down into the square root of 4 and the square root of 9. And we know the square root of 4 is 2, and the square root of 9 is 3. So 2 times 3 is then 6, which was the same as what we had before. So that again was just a little example to kind of show our product rule here. As well, other than the products, anytime that we have a radical of any index, so we'll say again that it's the nth index of, let's say it's x to the mth power, that is going to be equivalent to x to the power of m over n. So essentially we're just taking our inside power and putting it over the index, with our base still remaining the radicand. And that as well is going to be a nice property to keep in mind as we're working on some of these examples. Now, rules about radical expressions, we always want to simplify them down as much as possible. And a radical expression is simplified, quote unquote, when the index n is as small as it can possibly be. The radicand will contain no factors other than 1 that are nth powers of an integer or polynomial. And again, the n in this case is our index. The radicand contains no fractions, so there are no fractions underneath our square root symbol, or our radical symbol. And there are no radicals in the denominator. And that one we should remember, because we always said you never want a radical in the denominator. Whenever we have a fraction, you always want to get it so that the radical is up in the numerator. So that one shouldn't be anything new. So keeping these rules and these properties in mind, let's go ahead and work on a couple of these examples. In this first case, we have the square root. Again, remembering this is an implied radical of 2. So the square root of 25, a to the 4th, b to the 9th. Now there are a couple ways we can look at this. First, we can, again, recognize that this is the 2 index of the square root. So we would recognize then that we would call this, if this is 25 to the 1, 25 to the 1/2 power, a to the 4/2 power, keeping its the original power from before over the index, so 4 over 2, and b to the 9 over 2. This is a completely valid way to look at it, except for the fact that it's not always easy taking a number to a power that is a fraction. Technically, the value that it gives you is going to be correct, but really this only helps us with the a. In this case, 4 divided by 2, we know that that comes out to just 2, whereas the other ones don't come out so easy. But we at least know that our a to the 2 is correct. Another way to look at this then would be just to split them up into their individual pieces. So square root of 25, square root of a to the 4th, and square root of b to the 9th. Once we have it here, we can recognize that square root of 25 is 5, remembering from before, or recognizing that this is still the 2, we can recognize that we have a to the 4 over 2, which we determined was a to the 2, or a squared. Looking at our last piece, though, b to the 9th does not square root very easily. But what we can do is break this up into b to the 8th, or should I say square root of b to the 8th, times square root of b. In this case, it does break out much easier, because now that we have a square root of b to the 8th, again, we can recognize that as 8 over 2, or we can recognize it as b to the 4 squared, and when we're taking a square root of that, those cancel out, and we're just left with our b to the 4th. So in the end, our final answer for this one is 5, a to the 2, b to the 4, and we can't forget our radical b left on the outside. In this case, our radical b cannot be simplified anymore, so this is our final answer. Moving on to our second example, this time our index is 4. So we're going to want to make sure that we can get things down into groups where they are to the 4th power. So one thing we can recognize is that 16 is 2 to the 4th, and we're keeping our 4th radical over everything. X to the 5th we can rewrite as x to the 4 times x to the 1, or just x, and y to the 4th is already in a power of 4. All of these 4's will cancel out with this 4, leaving on the outside 2, x, and y, but this x to the 1 needs to remain as 4th radical of x because it didn't have anything to cancel out. So in the end, again, this final answer will be 2xy times the 4th root of x. And moving on from here, just like how we can take the product of numbers and split them up, we can also take a fraction of numbers or a division of numbers and split them up as long as we keep the same index. So we would split this one into square root of y to the 8th over square root x to the 7th. Now, square root of y to the 8th, again, we can recognize that as either, we can say y to the 4th squared, and we're taking the square root of it, in which case we cancel those out, or we can recognize it as y to the 8 over 2, which is the same as y to the 4th. Either way, y to the 4th, y to the 4th. So we know that our numerator, or our top number there, is going to be y to the 4th. Looking at our numerator, though, we have an square root of x to the 7th. We can break that one, remember, into x to the 6th times square root of x. From here, again, x to the 6th we can recognize as either x to the 6 over 2, or we can notice that that's going to be x to the third squared, and we're taking the square root of it, canceling out the square roots. We're left with x to the 3, or 6 over 2 is 3, so this one is also x to the 3. So our first part of our numerator is x to the 3, and we still have our times the square root of x to deal with. We're not finished at this point, though, because remember, we don't like having the radicals in our denominator. So if we want to get rid of a radical in the denominator, we're going to do a similar process to what we would do for finding a common denominator if we wanted to add or subtract fractions. Remember, we always just multiply by a form of 1. And in this case, by form of 1, we mean just a number over itself. In this case, we're going to want to use our radical fraction, or our radical number there. So we would want to use square root of x and square root of x. We want to do that because when we take the square root of x times the square root of x, well, square root times the square root will give you that number. So that'll get rid of the radical. That'll leave just x on the bottom. So if we carry this out and find our numerator, square root of x times square root of x is just x, times our x to the third power, we'll be left with x to the fourth. And on top we have y to the fourth and square root of x. Those don't really combine, so we're just left with y to the fourth and square root of x. So this is now our final answer. Moving on to our next example here. In this case, again, we want to break it up into cube root of 2, cube root of 9x. Now in this case, we want to recognize that 9x is the same as saying 3 squared x, because we have our 9, which is 3 squared, and just our x left. Now again, like in our last one, how we multiplied by a number to try to simplify the radical on bottom, we want to get our radical on bottom, in this case, to be a full number again. We want to get rid of that radical. But our index in this case is 3. So we need to make sure all of these numbers are a 3 that we're taking as a power for. So in this case, we need to multiply by a cubed root of, well, we already have 3 to the 2, so we need 3 to the 1. Or we can just notice that that is just 3. Also, we have x to the 1, so in this case we need x to the 2. Now that we have our denominator for our form of 1, our numerator is going to be the exact same. And noticing here that all of our indices, our indexes, are 3, we can just combine our terms as we multiply them across. So our numerator becomes cube root of 2 times 3x squared. 2 times 3 is 6, x squared. On the bottom, again, we have a cubic root of 3 squared times 3 becomes 3 cubed. X to the 1 times x to the 2, or x squared, that becomes x cubed, or x to the third power. And again, from here, we can recognize that we have cubic root of a cube and a cube. So those cancel out, leaving our denominator as just 3x, and our numerator cannot be simplified anymore, so it just becomes 6x squared. And so this is our final answer.